Welcome to a lesson on determining area using double integrals with polar coordinates. The area of a region defined in terms of r and theta can be found by using a double integral in polar coordinates. And we did this using rectangular coordinates where we had the double integral of the region r, where differential a was either dy dx or dx dy. And remember, in polar form we replace differential a with an extra factor of r dr d theta, where the limits of integration for r must be a function in terms of theta. Let's go and take a look at a couple of examples. Here we want to determine the area of one of the petals of this rose. We'll take a look at the graph of this on our calculator in just a minute. But if we know that r is equal to 2 sine 3 theta, so if we want to determine the area of one of these petals, we'll have the double integral and then r dr d theta. Well, we know r is equal to 2 sine 3 theta, so for one of these petals, the radius will start at 0, go out to the end here, and then come back. So we know r is going to start at 0, and it'll be traced out by 2 sine 3 theta. For the limits of integration for theta, we'll have to determine what interval for theta would trace out one petal. There's a couple ways of doing this. I like to use the graphing calculator to illustrate this, so let's go ahead and use that first. We know we have to be in polar mode, but I also find it easier to be in degree mode because it's easier to determine what angle is being represented. Let's go ahead and type in 2 sine 3 theta. And I've already set the window from -3 to +3. Let's go ahead and press graph. Now let's go ahead and press the trace key. Notice right now we're at theta equals 0. We're trying to determine what theta would be to trace out one of these petals. So if we press the right arrow, we can see it tracing out that first petal. And now it's coming back to the origin. And notice that it occurs at theta equals 60 degrees, which would be pi/3 radians. So the interval for theta would be from 0 to pi/3. And this will give us the area of one petal. Another way to determine theta would be if you know, now another way to get this interval by hand would be to take a look at the basic sine function. We know the period is 2 pi, so here would be at pi. So from 0 to pi, the sine function goes up to 1 and back to 0, which would represent one petal here if we had just sine theta, but we have sine 3 theta. So if we let 3 theta equal pi and then divide both sides by 3, notice we'd also get the interval from 0 to pi/3. Let's go ahead and integrate this. So we're going to have r squared over 2 so when r is equal to 2 sine 3 theta, we'd have 4 sine squared 3 theta, and then 4 divided by 2 would give us 2. So we have 2, 0, and we'd have sine squared 3 theta d theta. So now we need to use the power reducing formula for sine squared theta. So this 2 would simplify with this 2 here. We'll be left with 1 minus cosine double the angle, or 6 theta. Let's go ahead and finish this on the next slide. So here we'd have theta. The antiderivative of cosine u would be sine u, minus the antiderivative of cosine 6 theta. We'd have u equals 6 theta, du equals 6 d theta. So we'd have an extra factor of 1/6 sine 6 theta. Evaluate this at 0 and pi/3. So replacing theta with pi/3, we'd have pi/3 minus, well, the sine of this would be 2 pi, that's 0. And then minus this would be 0, and this would be 0 again. Pi/3 would be the area of one of these petals. We'll take a look at one more example in part 2.